This video has been brought to you by Limitless Learning TT, a holistic learning center. In this session, we will review number 3 of the May-June 2018 Paper 2 for Cape Pure Math Unit 1. To see more material like this, go to our website, www.limitlesslearningtt.com, hover over the Outreach tab and click Free Material. For more information about our services, you can also visit our website under Services. You can email us at info@limitlesslearningtt.com, or you can always give us a call at 868-620-1532. Please note that the actual past paper for May-June of Pure Math Unit 1 will be on the website as well under free material. So let's get started. Okay, so we have to show part A that sine of 2 theta minus cos of 2 theta plus 1 all over cos 2 theta plus sine 2 theta minus 1 is equal to sec of 2 theta plus tan of 2 theta. So when doing proofs, trigonometric proofs, the best thing to do is always start with the side that looks more complicated. It's a lot easier to simplify a complicated section rather than using something that's already simplified and trying to expand it. Taking that into consideration, then the best thing to do would be to start with the left-hand side. So first thing that I'm going to want to do is utilize our double angle formulas for both sine 2 theta and cos 2 theta. Now recall that sine of 2 theta is the same thing as 2 sine theta cos theta, and cos of 2 theta is the same thing as cos squared theta minus sine squared theta. So I'm just going to write that in, substituting those two values in for sine 2 theta and cos 2 theta to see what we're going to end up with. Okay, so I filled that out. The next thing that we need to do is basically distribute this negative sign to this and then to this one here. And what I'm going to end up getting is 2 sine theta cos theta minus cos squared theta plus sine squared theta plus 1. And then at the bottom, the same thing from before. Now what I'm going to do is try and simplify the denominator one time. I am going to use the fact that sine squared theta plus cos squared theta is equal to 1. And so I'm going to replace this one here, as in this one here, with sine squared theta plus cos squared theta. So on my denominator, I'm going to have cos squared theta minus sine squared theta plus 2 sine theta cos theta minus, don't forget your sine, sine squared theta plus cos squared theta. Right, now again I'm going to multiply this negative sign here and then here, and so I also want to do, because I'm trying to not run out of space as well, I'm going to do the same thing on the top for 1 as well, as in this one here. On top, I am also going to replace that with sine squared theta plus cos squared theta. Right, so now I can go ahead and expand everything and also group terms that are like together. So let me start with the numerator first. I'm going to switch to another color just so that we don't get confused. 2 sine theta cos of theta minus cos squared theta plus sine squared theta, and then this now becomes a plus sine squared theta plus cos squared theta. This is my numerator, right? And then I have this negative cos squared theta and this positive cos squared theta. That's going to cancel each other out. And then this sine squared theta plus another sine squared theta, that's just going to give me plus 2 sine squared theta. So on the top, now that I've expanded that and group like terms together, I am going to end up with plus 2 sine squared theta. Right, so that was my numerator. Denominator now, I am again grouping like terms together, so, well, not grouping as yet. I'm going to expand first. Cos squared theta minus sine squared theta plus 2 sine theta cos of theta. When I take out the, when I expand the negative sign and the brackets, I get minus sine squared theta minus cos squared theta. And that's going to help because some of my terms are going to cancel out. So once again, this cos squared theta here is going to go away with this minus cos squared theta. And then I'm going to have minus sine squared theta and a minus sine squared theta here. So I end up with kind of like the same thing that's on top, except the sign between them has changed. So my numerator has 2 sine theta cos theta plus 2 sine squared theta. And my denominator is going to have 2 sine theta cos theta minus 2 sine squared theta. So I'm just going to go ahead and fill that in. Right, and again, I want to make sure that how I'm working down, that I'm also going to get back to my right hand side. So quick tip, if you know what your right hand side is supposed to become, sec theta is the same thing as 1 over cos. So this is really 1 over cos of 2 theta, and tan theta is the same thing as like sine of 2 theta over cos of 2 theta. So basically, I want to get down to something that's either the black side or something that's the yellow side, yellow, because the yellow will be the step right before black. All right, so where I'm at right now, I now have things in terms of sine theta and cos theta. So what I want to do is pull out any term that is like. So each one of these terms on both my numerator and denominator have 2 sine theta that's in common. So I can simplify this to pull out the 2 sine theta. And so what I'll be left with on top is cos theta plus 1. Sorry, not cos theta plus 1, cos theta plus sine theta. Okay, and then on the bottom, when I pull out 2 sine theta, I am going to have on the bottom cos theta minus sine of theta. Okay, so I'm going to rewrite this step here on the next slide, just so that, you know, we have more space to work with. Actually, before I do that, I can cancel this off and this off, right, because those are in common, and basically what I'm left with is cos theta plus sine theta over cos theta minus sine theta. So that's where I'm going to continue from. Okay, and so many people, when they get to this step, they get stuck because this doesn't look anything like what's in yellow or anything like what's in black. But the nice thing about proofs is that you can literally introduce anything into this expression as long as you're multiplying by 1. And why that is nice is because you can choose anything to be 1. Remember, any number over itself is 1, any expression over itself is 1. So what I'm actually going to end up doing is multiplying by 1, but I am going to choose what I call a nice one, right? A nice expression over itself. And the expression that I'm going to choose is going to be my numerator, cos theta plus sine theta over cos theta plus sine theta. Now, you may be wondering, why am I choosing that as the one that I'm going to multiply by? And it's simple. Knowledge of difference of two squares, if you remember this. A squared minus b squared is the same thing as a plus b multiplied by a minus b, right? In this case, right, this is my a here minus b, and this is my a plus b. So when I multiply these two factors by each other, I'm going to end up with cos squared theta minus sine squared theta, and that looks a lot like cos 2 theta. Ta-da! Right, so there's a method to the madness. Right, so now what we're going to do is expand this. So on the top, I'm going to have cos theta plus sine theta multiplied by itself, right, which is cos theta plus sine theta. I just told you on the bottom, this is a difference of two squares. So what I'm actually going to end up with is cos squared theta minus sine squared theta. And cos squared theta minus sine squared theta is going to give me cos 2 theta. So I can replace this now with cos 2 theta. Now, on to my numerator. For my numerator, I'm going to have to FOIL out this. So, this by this by this, and then this by this, and this by this. So, for my numerator, I am now going to get cos squared theta, right, plus sine theta cos theta, plus another sine theta cos theta, which will give me plus 2 sine theta cos theta, and then my last term will be plus sine squared theta, and again this is over my cos of 2 theta. Right, now again I am going to use the fact that sine squared theta plus cos squared theta is equal to 1. So I'm now going to replace those two terms with the number 1. So for my numerator, I now have 1 plus 2 sine theta cos theta. And then again, I remember from my double angle formula that 2 sine theta cos theta is the same thing as sine of 2 theta. So I can replace this now with sine of 2 theta. And now I have something that kind of looks like what's in yellow. I just have to break up my fractions. So what I have now is 1 over cos of 2 theta plus sine of 2 theta over cos of 2 theta, which is exactly what's in yellow, to give me now sec of 2 theta plus tan of 2 theta, which is my right-hand side. So I have effectively shown that I can move from my left-hand side down to my right-hand side. And again, the trick in this proof would have been knowing what is your 1 that you're going to multiply by, right? Which expression over itself you're going to choose to multiply by, and the knowledge of difference of two squares. And again, this is kind of something that you really get with practice. The more trigonometric proofs that you attempt, the better you'll get at it. Right, so that was 3 part A. So now we're going on to 3 part A, part 2, which says, hence or otherwise determine the general solution of sine theta minus cos theta plus 1 over cos theta plus sine theta minus 1 is equal to 0. So usually when they say hence, it means that you really want to use the point, the part from before. So what we want to solve now is sine of theta minus cos of theta plus 1 over cos of theta plus sine of theta minus 1. We want to find the general solution for that when it's equal to 0. And so basically this is the same equation above, like what we got for A part 1, except 2 theta. So the 2 thetas that you see everywhere is really going to be replaced with theta. So basically, this equation is the same thing as sec of theta plus tan of theta. And again, we're trying to solve for when this is equal to 0. So I'm actually going to use this portion that I would have gotten from A part 1. This is my hence part, and I'm going to use this to get the general solution. So the first thing that I want to do is replace sec theta with 1 over cos of theta, and tan theta with sine of theta over cos of theta, and that's equal to 0. This is what I want to solve. Basically, if I combine these two fractions, I end up with 1 plus sine theta over cos theta because my denominators are the same. So I just have to combine the numerators. So this is the same thing as 1 plus sine of theta over cos of theta. And I want to solve for this equation. I need to get rid of my denominator. But whenever you have what's like a variable or function in the denominator, you always want to multiply by your denominator squared, just so that you do not lose a solution set. So I am going to multiply by cos squared, and so that's going to give me 1 plus sine of theta times cos of theta. 0 by anything is 0. So I multiplied by cos squared theta so that I don't lose a solution set. Now that I have these in factor form, it means that 1 plus sine theta is equal to 0, or cos of theta is equal to 0. If 1 plus sine theta is equal to 0, it means that sine of theta is equal to negative 1. I'm just going to rearrange the equation. And then if sine of theta is equal to negative 1, it means that theta, the critical value, or not critical value, what's the term is escaping me now, the value of theta that's between 0 and 2 pi, right? So that's gonna be 3 pi over 2, or because we're working in radians, right, which is the same thing as like 270 degrees. And then the same thing for theta will be cos inverse of 0, which the value between 0 and 2 pi would give you pi over 2. But that's not what the question asked for. The question asked for the general solution. So basically, it's any value that's pi over 2 plus or minus 2 pi, and then the same thing for 3 pi over 2 plus or minus 2 pi. But I can combine these two solution sets and create just one general solution. So my general solution will actually be, I'll take the smaller value, which is pi over 2 plus or minus n times pi. And so the reason I'm choosing this is because when I add n times pi to pi over 2, I will pick up these values. Right? Sorry, not these values. Whoops. I will pick up these values. So let's just look at it, right? So when n is equal to 0, my solution is pi over 2. When I'm looking at pi over 2 plus n pi, right? When n is equal to 1, I'll get pi over 2 plus pi over 2 plus pi, right? Which is the same thing as 3 pi over 2. Then when n is equal to 2, I am going to end up getting pi over 2 plus 2 pi, which is in this solution set, right? And then again, when n is equal to 3, I'm going to get which is in this solution set. So putting this big general solution here in yellow combines the results from when theta is equal to 3 pi over 2 plus or minus 2 pi, and also takes into account when theta is equal to pi over 2 plus or minus 2 pi. So my final general solution is pi over 2 plus or minus n times pi, where n is any integer. So that is taking care of number 3, part E. Now let's move on to number 3, part B. Okay, so it says, given that cos of A is equal to 3 over 5, and that sine of B is equal to 3 over 4, and A and B are acute angles, calculate sine of 2A. Well, double angle formula, sine of 2A is the same thing as 2 sine of A cos of A. So we know what we know what cos of A is, but we don't know what sine of A is. And we can actually figure this out pretty easily if we think about a right angle triangle and let this angle be A, right angle triangle. Cosine means that it will be adjacent over hypotenuse. This is your hypotenuse, so that will be 5. This is your adjacent side, so this will be 3. And this is a Pythagorean triplet, which means that this side here is 4. Or if you use Pythagoras' theorem, 3 squared plus the other side squared should give you 5 squared, and that's going to result in 4. So therefore, sine of A will be opposite, which is 4 over hypotenuse, which is 5. So now I can replace that into here. 2 times sine of A, which is 4 over 5, multiplied by cosine of A, which is 3 over 5. And so 2 by 4 is 8, 3s are 24. And then 5 by 5 is 25. So sine of 2A will be 24 over 25. Part 2 of B asks us to find cos of A plus B. And again, this is the straightforward compound angle formula, right? So compound angle formula for cos of A plus B is the same thing as cos A cos B minus sine of A sine of B. So again, we know what cos of A is. We can replace that with 3 over 5. We know what cos of B is. No, we do not, but we will find it shortly. Minus, we know what sine A is. We just found that it's 4 over 5. And we know what sine B is. It is 3 over 4. So to find cos B, we're going to do the same thing that we did triangle-wise. So let's say that we have a triangle, right angle triangle. This angle is B. We know that sine of B is 3 over 4. Sine is opposite over hypotenuse, which means that this is your opposite side of B, and this is your hypotenuse, which is 4. Using Pythagoras' theorem, this side, let's call it x. X squared plus 3 squared should give you 4 squared, which means x squared plus 9 should give you 16. X squared plus 9 would give you 16, which means x squared should be equal to 5, and x is equal to square root of 5. So it means that this side here is the square root of 5. So therefore, cos of B is going to be adjacent, which is square root of 5 over 4. Right? So they have the same denominator, which in this case will be 5 times 4, which is 20. And our first term will be 3 times the square root of 5 minus, and then 4 by 3, which is 12. So final answer, 3 root 5 minus 12 all over 20. So that is the end of B, right? Part 1 and part 2 of B. And then the final question is to solve an equation for a specific range. So we have to solve sine theta minus the square root of 3 times cos theta equal to 1 for theta between pi and negative pi. Alright, so attached to cos theta is a little complex, so I am going to carry that over to the right hand side. So I'm going to be left with sine theta on the left is equal to 1 plus the square root of 3 cos of theta. Then I am going to basically, my issue is that I have one equation with 2 different functions. There's a sine theta and there's a cos theta. Now, I can replace either sine theta with cos theta or cos theta with sine theta using my identity sine squared theta plus cos squared theta is equal to 1. But that means that I need to square them in order for me to be able to use that identity. So I am going to square both sides. That will give me sine squared theta is equal to 1 plus the square root of 3 cos theta by itself, squared, right? And so if I'm squaring that, it just means I'm multiplying that term by itself. So 1 plus square root of 3 cos theta. So I'm going to replace sine squared theta with 1 minus cos squared theta. Right, and now I can expand these 2 parentheses. So 1 by 1 will give me 1. 1 times the square root of 3 cos theta will give me square root of 3 cos theta. And then I multiply square root of 3 cos theta by 1. It will give me that same term, so that twice, which is now plus 2 square root of 3 cos theta. And then lastly, I have to multiply square root of 3 cos theta by itself. So that will give me square root by itself gets rid of the square root. So that gives me 3 cos squared theta. So now I'm going to put everything on one side, and let that be equal to 0. So I'm carrying this cos squared over to this side, so it's going to become positive, and I'm also taking the 1 over to this side, which will make it negative. So what I end up with is 0 is equal to 1. That 1 becomes minus 1. Then I have my plus 2 square root of 3 cos theta plus 3 cos squared theta, and then that minus cos squared theta becomes plus cos squared theta. Right? 1 minus 1 gives me 0. And then 3 cos squared theta plus cos squared theta gives me 4 cos squared theta. So what I have is 0 is equal to 4 cos squared theta plus 2 square root of 3 cos of theta. And I can pull out anything that is a like term. So I'm gonna choose to pull out cos theta. I can actually pull out 2 cos of theta, to be quite honest. 2 cos of theta. What I'll be left with in here will be 2 cos of theta plus root 3. Right? So now this must mean each of the 2 factors are equal to 0. Either I have 2 cos theta equal to 0, or I have 2 cos theta plus square root of 3 is equal to 0. Once I rearrange that, I am going to get on this end that cos of theta is equal to 0, and the only place that cos of theta is equal to 0 within my range, theta has to be negative pi over 2 and pi over 2. Right? And then for this one now, cos of theta will be equal to, I'll carry the square root of 3. On the next side, it becomes negative square root of 3, and then divide by 2. And so the only time I'm going to get negative square root of 3 over 2 within my range is when theta is equal to negative 5 pi over 6 and 5 pi over 6. Remember that cosine is a symmetric function in the y-axis, so whatever you have on the right hand side is going to be on the left hand side. It's also a good idea to kind of have knowledge about how these graphs look. It's going to make it a lot easier to pick up your solutions if you're in time constraints on an exam. Right? So what we just completed was number 3. This is from module 2 of the May-June 2018 paper 2 for Pure Math Unit 1. And again, this video has been brought to you by Limitless Learning TT, a holistic center. If you're looking out for more material like this, additional videos, you can check our website, hover over the Outreach tab and click Free Material. You can also find our videos on YouTube as well. And for more information about our services, you can also check out the website. That's limitlesslearningtt.com. You can always shoot us an email at info@limitlesslearningtt.com or give us a call at 610-1532, country code 868. Thanks, guys.